Okay guys, now this might be a good time for you to drink a strong cup of coffee or do some kind of physical exercise for a little bit because we're about to venture into a pretty complicated element that you need to learn to understand inferential statistics. And I'm going to do my best to put this simply, but you actually might need to go over this in some more detail on your own in order to fully grasp it. But I'm going to give it a shot. So what I'm going to be talking about right now is the central limit theorem, which is the basis for all tests of means. And when I say tests of means, I mean when you're trying to ask the question, does the mean for this group differ significantly from the mean for some other group or from the mean of the population? And there are a few things that we know about distributions of means, okay? Now, I just want to clarify, up till now, I've mostly been talking about distributions of individual scores. So that, for example, when I drew the normal curve and I talked about your comp score, for example, and I said if your comp score was one standard deviation above the mean, then you were the 84th percentile. That's all talking about individual observations. But there's another distribution called the sampling distribution, which is a distribution of all possible sample means taken from a sample. And so there are some principles that you need to keep in mind when you're asking the question, what would a sampling distribution look like? Remember, a sampling distribution is a distribution of all possible means of a sample. First of all, the sampling mean will equal the population mean. Okay? Secondly, the curve will be normal. And then, thirdly, the standard deviation of the sampling distribution, which is called the standard error, by the way, is related to the standard deviation as follows by this equation. Now, I'm not expecting people to memorize equations, but I do think it helps to just take a look at this, okay? This symbol means the standard error, which is the standard deviation that you would find if you graphed all of the possible sample means from a particular sample. I'm sorry, from a population. And here you have the standard deviation divided by the square root of the sample size. So what this means, that the sort of take-home message here is, as your sample size gets bigger, your standard error gets smaller. And I'm going to show you a graphic representation of that I think will really drive this point home. But just remember this formula. As n, which is your sample size, increases, your standard error decreases. Here's a picture that I think will help you understand that. Let's say that we're doing an experiment asking the question about the IQ of sex offenders. And so we get some sex offenders, but we don't have unlimited resources, and we're only able to gather up 15 sex offenders, okay? Look at this curve, okay? See how it's this long, sort of sloppy curve? That's because it has a huge standard error. And the reason for that is we have a small sample size. So let's say that the mean of our sex offenders in terms of IQ is 85, and the mean of the population is 100. Well, that does seem like a substantial difference, but we actually don't know if it's a significant difference unless we run some a statistical procedure. But if you just eyeball it, what you'll see is that there's a lot of overlap between our small sample size sampling distribution and our population distribution, such that I think it would be hard to say with certainty that there's a significant difference between those two groups. Now, let's say that we get a grant, and we're able to spend the resources to get 45 subjects. What that does is it significantly narrows our distribution of means, instead of having a fat and sloppy sampling distribution, we now have a very lean, athletic sampling distribution, which clearly does not overlap very much with the population. Okay? So the take-home message here is that the central limit theorem tells us that the bigger our sample, the easier it is to find significant differences when they actually exist between our sample and the population, and that the sample mean, or the sampling distribution mean is going to be, we're going to be more confident that it is reflective of the population mean that we're looking at. Okay, and I apologize if that kind of went over your head. Don't feel too bad. I actually took statistics for a year and didn't understand that point. And it was one of those aha moments where I finally recognized, oh, the sampling distribution of means is totally different than the sample distribution. And the standard error is not the same as the standard deviation, but these concepts are related to each other. But I think you can feel good if you understand that the simple point that the bigger your sample size, the more it draws your sampling distribution into a narrow shape, which allows you to observe actual differences when they are occurring between your group and another group or your group in the population.